Okay. Okay. Hello, I am Brian Wheatman, and today I'm going to talk about some recent improvements to packed memory arrays. And this is work I did along with Helen. Okay. So first, what is a packed memory array? A packed memory array is an ordered dictionary data structure. So in addition to the sort of insert, delete, find queries we heard of before, now you also might want to support next, previous, or range query. By range query, I mean you're going to give two keys and you wanted to find or do something with all elements that have value between those two keys. So specifically with the packed memory array, this is going to store n elements in order n space, support inserts and deletes in log squared of n amortized time, point queries in log n. But the real idea behind the packed memory array is it has extremely efficient scans. The way these scans are so efficient is that the entire packed memory array is stored in a single allocated block. So all of the memory is continuous. Roughly how it works is you allocate one large block of size O of n, and then you're going to intersperse your elements amongst that block. So you have short runs of elements and then spaces. Then whenever you want to insert a new element, you can simply put the element where you want to, shuffle around a small number of elements to maintain space. To ensure that you can always do this, you're also going to maintain a set of densities so that no region of the PMA gets too sparse or too dense so that you can keep adding new elements. I show it up here both on the bottom as a continuous memory and on top as a tree. We will often think of the PMA sort of logically as this binary tree, where each leaf of the PMA is sort of controlling these roughly log n cells. So we have a tree of height roughly log n with n over log n leaves. However, all of the memory is stored continuously, and it is just this logical tree. Okay, so just a review of the theoretical behavior for the PMA compared to the B tree and the binary tree. The things that jump out at us is sort of both the insert and the contains are worse than sort of the theoretical optimals that you can achieve with the B tree. And they're worse by sort of this either log factor or log versus log B factor. Then we're going to look at sort of some of the empirical results. And what we see is sort of, as I said before, we get our scans, where your scan is just read over. Yes. So this is going to be memory transfers in the external memory model. And then if we look at sort of our empirical results, what we're going to find here is, as I said before, our PMAs are extremely efficient in scans, about twice the speed of that of a B tree. However, our finds are about half the speed, our inserts are about 3/4 of the speed, and we're bigger. So in summary, we have our excellent scans, and we have our three issues. They're big, they're slow for point queries, and they're slow for inserts. So the remainder of this talk is going to be fixing these three things. We're going to speed up our point queries. And by speeding up our point queries, we're also going to speed up our serial inserts. It turns out a decent amount of the time in serial inserts is just finding where that element needs to be inserted. Then we're going to add parallel batch inserts. This will allow us to speed up inserts even more for parallel batch workloads. And lastly, we're going to decrease the size of this thing. I'm going to first talk about some work on a search optimized PMA, and this will sort of speed up the point operation. So we're going to maintain our scan performance and dramatically improve both our find and our insert times. So before I can do that, let's go a little bit into how we search in a PMA. As I said, it's basically an array with extra spaces. Roughly, we just have to do a binary search. What we can do is while we insert and we're shuffling around elements, we can maintain the fact that the first element of each leaf will always be an element, not a space. This allows us to just do a binary search on the first element of each leaf. Then once we figure out which leaf the element may or may not be in, we can just do a scan over that leaf. These leaves are guaranteed to be of log n size, and so we don't really need to worry about the cost inside of them. So diving into this a little more, we do our standard binary search, and then we get to the bottom. Initially, each of these steps along the binary search is very likely to be a cache miss. These leaf heads are of distance log n apart from each other. However, at equilibrium, we're going to end up storing some, high part of the tree in cache. However, even when we're storing these high parts of the tree in cache, we're getting sort of a small amount of useful data. In each cache line, we're really only going to store the first element of that cache line where we're useful, and the rest of it is not very commonly used. This is just whatever data happens to be in the same leaf as the pieces on the high parts of the binary tree. But we do end up saving a few steps in our binary search. So the general idea around a search-optimized PMA is that we end up with sort of two parts of data. We have our leaf heads, where we're going to want to be able to very efficiently query, and we have the rest of our data where we want to be optimized for these scan-based workloads. And so what we end up doing is we can move all of these heads into a separate data structure that is faster for querying and sort of leave the rest of the data as it is to give us our efficient scans. So let's look. We're going to start with sort of just a standard linear thing. Here we're going to basically take these first elements of each leaf, move them to the side, keep them in the same order. So now when we do our binary search, we notice two things. The first is that the last few steps are now going to all be within cache. We're doing a binary search, and these things are all now very close together. So we're going to save an additional log b factor at the end. However, we are going to pay an extra 1 cost because now we need to go load the data, which is now somewhere else. And once again, as we do repeated searches into these structures, we're going to again save the first log m over b steps. However, here, the elements nearby these are more likely to be useful elements because these will all be other things that will have to be searched through at some point. So now let's look at some empirical performance for these. So here I have search throughput on the left as we perform lots of searches into the structure, and serial inserts on the right, where in both cases we're measuring throughput, so up is good. We're comparing sort of a traditional B tree in blue to a traditional B plus tree in black, and the search optimized PMA in yellow. What we see is sort of across all ranges of sizes. For searches, this optimization that we have performed with moving the heads to the side has allowed the search optimized PMA to outperform B plus trees, which again have this asymptotic benefit over PMA, over even the search optimized PMA across a range of sizes of the structure. And similarly with insert, here we don't quite dominate the B tree for the smaller sizes, but we do for all other sizes. Now this is quite good, but we do notice sort of right at the top for the biggest structures that the search optimized PMA starts to decrease its benefit over the B tree. And one big reason this is the case is that we have sort of what is the total size. One of the benefits of the search optimized PMA is that you're moving all of these heads, these highly queried things, into this separate, smaller structure. And turns out for a very wide range of data structure sizes, that side structure just fits in cache. The size of these head structures is a log n factor smaller than the total size of the data. And so up until almost 1 billion elements, they just fit in cache. And this is kind of why once we hit about 1 billion elements, we no longer see this advantage. But we can do better. There's no real reason we need to, there's no major reasons that we don't need to, that we need to keep the heads in the same relative order as we keep the data. We do need some things about it so we can maintain our scan performance, but we can use what is known as Etzinger order. This is a heap style order where we basically take the root of the tree, put it at the beginning, and then put the two children of each node at positions 2i and 2i plus 1. The main benefits of this approach is actually the fact that it's very predictable to the memory system. Given any node, if we're certainly currently querying some node, the next place we're going to search is either at 2i or 2i plus 1. And so sort of wherever the branch predictor guesses, whichever one of these cells ends up getting loaded, the right cache line is highly likely to be loaded. And this gives us sort of very predictable access and thus very efficient access. And we find that this performs quite well. And here we see across the whole range of sizes, we get a sort of similar additional benefit over even the linear heads on search throughput, and we no longer deteriorate as we fall out of cache. The Etzinger heads are just a little bit bigger than the linear heads. And similarly with insert, we again sort of get a fairly consistent speed up across all ranges of sizes once again. The next thing we could do is actually put our heads in a B tree style order. This is a static B tree order. where we take our blocks of data and again do heap style order. However, this way we can do blocks of size B. This way, each time we do a load, again on our external memory model, we can grab the next log B levels, dividing our total cost by log B. And so now if we look at our asymptotic performance, again in the external memory model, we find that sort of we have in red this traditional bounds of the PMA. We have in green sort of the optimal bounds we'll get from a B plus tree. And we find that with the SPMA B tree, we are able to achieve hitting optimal bounds for both search and range queries. However, we haven't impacted inserts at all, so we do still get a slower bound there, other than the improvement that we get in the search phase. Now, if we look at the empirical performance, we actually find that the SPMA B tree doesn't get us that much additional benefits over at single order. In either case, but perhaps it does for the largest cases or larger than I can run in memory. Okay, so any questions about search optimization and faster searches, or I will move on to parallel batch inserts.
They're all happening in batches. All the updates are happening in batches?
So in this phase, the searches are happening, just sort of a bunch of them are happening in parallel as sort of a giant batch. The inserts at this point are all serial inserts. I'm about to move to parallel batch inserts, but this is all serial inserts. Anything else about searches? Okay. So I'm now going to talk to parallel batch inserts. But before I can really talk about parallel batch inserts, I want to go over how a standard serial insert works, just to contextualize the step. So with a PMA, we're going to break our insert into 4 phases. The first phase is going to be the search, figure out where on the PMA it has to go, mostly just which leaf it's going to be in. Then we're going to place the element in that leaf, possibly shifting around a few nearby elements. After this, we're going to sort of count up, see if that region of the PMA violates any of its density bounds. And lastly, we'll sort of find the smallest region that doesn't currently violate any density bounds and rebalance all of the elements in that region to maintain an even density within that region. So the parallel batch insert algorithm starts by sort of merging in the elements to the respective leaves. So here we have the PMA on the left and the batch on the right. I'm going to assume the batch is sorted. If the batch isn't already sorted, sort before you run the algorithm. I've also color-coded the batch to see which leaves these batches will eventually go to. The algorithm does not get that. So the first step is going to be simply find the middle element of the batch and figure out which leaf in the PMA this element goes to. The next step will be finding the first element in the batch that goes to the same leaf as the middle element of the batch. After that, we're going to take those elements from the batch and just merge them into the leaf. Then we can recurse on each half. So this batch merge algorithm gives us 2 nice properties. The first is we can very quickly get significant parallelism as we constantly recurse down and get sort of 2 new tasks for each one. And the other is that we end up saving work here. In a sort of standard approach of inserting a bunch of elements to a PMA, you have to do search for each element you need to insert. However, in this approach, we only need to search for at most 1 element that goes to each leaf. Additionally, as we recurse down the tree, the amount of space we're searching in the PMA also gets smaller and smaller. However, I skipped over a step. Sometimes you want to insert, a range of elements all to the same leaf, and they don't fit. This will never happen in serial. When you maintain your density bounds, you can always ensure that you can always fit the 1 additional element you want to do. Also, you can always just shuffle into your neighboring leaves to rebalance. However, during a batch merge, 1, you might insert a significant number of elements all to the same leaf. And second, because parallel modifications may be going on around you, you can't share any space with your neighbors. And so what we do in this case is we simply temporarily store these elements out of place. And in line with the PMA, we just sort of store a pointer and a count of how many elements we're currently storing. And this will be cleaned up in a later phase during the batch insert algorithm. The next step is to find the overfill nodes of the PMA. which regions are going to be needed to be redistributed. So the standard way to do this is we simply look at each leaf that was modified and walk up the tree to figure out which node of the PMA doesn't violate its density bounds. So for example, here, you can see my mouse, yes. With this node, we would check if this node violates its density bound, and it does, and then we would check this node and find it does, and it'd be fine, and then move on to each other path. The tricky part is that if you start trying to do this in parallel, you end up having some issues. Because while serially, if you just sort of cache the count of every node once you count it, you'll never count a node multiple times. However, in parallel, if you try to do this, it's possible multiple threads will all sort of count and check a single node before it has the opportunity to be finished and cached, and thus you can end up doing extra work. So the idea here is how can we develop a work-efficient counting algorithm that counts every required cell exactly once. So we do no extra work compared to serially inserting the algorithms. So the main idea here is to move level by level down the tree. So we start by now looking at sort of just the leaf level for each leaf that was modified and count. We want to check which of these violate their density bounds, count all the things, and then move up the tree for the ones that have violated their that maintain violating of their density bounds. And we do this until we reach a node. Now, whenever you find another node that has been counted, it will always already have been cached because it was done in a prior phase. So in summary, we're going to process the levels of the PMA tree serially. However, we can process all of the nodes at each level in parallel, and we can count all of the elements of each node in parallel as well. Now some more empirical results. What sort of insert performance do we get? We see here we're measuring the batch insert performance as we vary the batch size. What we find is in blue for a standard serial PMA, so this is running the parallel batch insert algorithm on a single core, we actually achieve a 2.5x serial speedup just from all the work savings that we get from the batch insert algorithm. And we get 47x total speedup on the parallel batch insertion, which sounds great until I tell you that we ran this on 128 threads. And 20x parallel speedup on 128 threads is not great. So what is the issue? The issue here ends up being memory bandwidth bound. We simply run out of the amount of memory we can transfer across this machine. And so what is the answer? We have to make our data structure smaller. So let's start with the easy thing. With a PMA, at some point, the root node, the whole thing is too full. And we have to grow the whole structure. The standard approach to this would be a table doubling approach. When you get full, double the size. But in theory, there's no reason we need to double the size. We simply need to multiply it by some constant factor. Now, a standard assumption here might be as the growing factor, however much you grow it by each time, gets smaller, you're going to end up paying a little more in insert because your data structure will maintain denser, so you'll have to shift around more elements, as well as it will be more common that you have to grow the entire structure. However, what we find here is if we look at the blue line, we can see our normalized insert performance, is that for a little while, as the data structure gets smaller, the inserts actually maintain getting faster still. This is because the whole data structure just stays smaller, and it is sort of less data that needs to transfer around. Similarly, we can see the size and the scan time just get faster and faster the smaller the data structure gets. However, once the growing factor goes below about 1.5, it does start getting slower again. However, with a lot of the work with the PMA, we care more about its sort of scan performance than we care about its input performance. So the experiments here are all going to show with a growing factor of 1.2, where we get pretty good insert performance and very good scan performance. But we can do more than that. We can also compress our data. The PMA is an ordered data structure, which means all of our data is also stored in order. This gives it very easy for us to use delta compression. So we take each leaf and individually delta compress them and store the elements using bytecodes. And we're able to substantially compress this data, making it even smaller. If we look at sort of the general sizes here, if we start with storing 8-byte integers, in general, we're going to store about the standard PMA will use about 16 bytes per element, growing factor of 2, 8 bytes per element, easily doubles to 16. Once we reduce that growing factor to around 1.2, we'll get a size of about 10 bytes per element. And then if we compress them, depending on the compressibility of the data, in this case, it's uniform random 40-bit elements, we end up getting about 3 to 4 bytes per element. And we get sort of what we wanted. Here we see our scalability plots. So we see from 1 core to 64 and then 128 hyperthreads for both the batch inserts and range query workloads. And we find that we're able to about double our scalability once we use the compressed data as opposed to the uncompressed data. Additionally, we can see here sort of stronger evidence that the fact that we were memory bound before, with the fact that the uncompressed PMA gets no additional speed up from hyperthreads and it just completely flattens out. However, the compressed back memory array is able to take advantage of the hyperthreads. Sometimes when you add compression, you are able to get better scalability at the price of not getting any more throughput because of the extra work of compression. However, we do find here that we're able to get about a 2x speed up on batch inserts, as well as a 1.3x speed up on range queries. Now to compare to some other existing work. So here we compare to 2 other batch parallel sets. Here I'm comparing to CPAC trees and P trees. CPAC trees are a cache optimized batch parallel set, and P trees are a binary tree with support for parallel batch updates. And we see across all ranges of batch insertions, as well as all ranges of query sizes, we're able to outperform these other existing works. Similarly, when it comes to size, while the uncompressed PMA is bigger than the cache optimized trees, the compressed data structures are both roughly the same size. Thank you very much. Altogether, we've sort of seen today that packed memory arrays are an excellent choice for ordered sets. And all of the code for my implementation of packed memory arrays can be found here. And any questions?
Now, suppose I use would say, well, now I keep by right? And how far would you then get? For example, I know in databases it's a known trick to use large or leases than you should. Then your scan performance should get very close to what you have in your PMA. Particularly if you then also start compressing the leads. My impression is that if you tune everything, then it converges to the same thing.
So not quite. You can. I have some other work actually at the poster session later today talking about B trees with large nodes. And what you find is you can do larger and larger nodes for B trees. In memory, you sort of will max out your insert performance at around 1K nodes. If you start going bigger than that, you'll also start decreasing your insert performance. For database, you can use. Yeah, I'm talking just the leaf nodes here. And you can make these bigger and bigger. However, you don't actually run into optimal scan performance until you have node sizes of hundreds of K to sometimes even megabytes, depending on what architecture you have. And that gets a little too big for B trees to manage.
Thank you.
Yeah. Yes. Any other questions?